All right, welcome to EE123 DSP Lecture 11. Woo! So today we're going to finish talk about time frequency. There are some examples that I didn't show you last time, and I decided in this class is that we put a lot of effort to making those labs for you, but we also want you to get something out of them. So we're going to spend in lecture, maybe half a lecture for each lab, explaining what is really the lab about, what are the steps they need to go through, so it will help you understand when you go through what would they actually mean. And so today we're going to cover Lab 1 and Lab 2, which you're going to get on Friday, and we'll be submitting on Friday. So we decided to give an extension to Lab 1 for Sunday night, and the reason is because, same midterm in the lab, same day, soft spot, something happened, and I think with age I become softer. But I think it will make it easier for you to finish. The whole idea is that you finish it, okay, and you do it well. Because I think that's part of this class that you get a lot from. Lab 2 is going to be out this Friday, though, and will be due next Friday. Okay, so and the Lab 2 requires the use of the software-defined radio that you got. Everybody got them? Okay. Midterm, don't forget, 3 to 5 p.m. this Friday. Be on time. Open everything. We're going to do it in class. For those who have conflicts, make sure to email all the staff, me and the TAs, and we're going to collect all of those, and we're going to send you information where the exam is going to be and what time to show up. Okay? Any questions? Yeah. March 12th. Okay, March 12th from 7 p.m. till I think not midnight, but probably 11. Something like this. So it's going to be in the WAS. Okay. I'm going to give you more information this week of how to register for the exam. I'm going to send a list of all the students in the class that you're going to have priority of taking it, and you need to say if we want to also take the general exam as well. But there's going to be one take. You're not going to be able to take it twice if you fail the first time. You'll have to find another session to get a license. Okay, any questions? Okay, so, what? Yes, and I'm sorry that I didn't do it yet so far. It was always out of my, just my context. I had to context switch and forgot. So I'll post them, yeah. I want to talk about ham only when on Tuesday evening when I talk about ham, if that's okay. I spend 2 hours, on that extra, so I don't want to steal from the actual class. But you can definitely read online about what's the difference. So we talked last time about spectrograms, and we talked about the short time Fourier transform. And when you look at a spectrogram, there's the time and then the frequency space. So you map a one-dimensional signal into a two-dimensional space. Okay? So you start with one coefficient, which is the index, and then you get two coefficients, which are the time corresponding to time. There's still indexes, but corresponding to time. And then there's another component, indexes corresponding to frequency. And it gives you very interesting information about the signal. Now it's much more complex because signals that are not stationary in frequency nor in time, you might be able to capture this and do a lot of interesting things with this. In looking, obviously, this is not a speech signal. This is a bird, and so you can see it's dynamic. It's quite complex. So the discrete time-dependent Fourier transform is how you calculate this, and it's expressed using this sum. And if you fix R to be, for example, 0, you just get the DFT, okay, of a window of size L. Okay, so 0 padded DFT of size L, and that's simple. For different R's, you would get basically a window that captures different parts of your signal. So you basically decompose your signal into chunks, blocks. And the way that this is written is that the window is fixed and the signal is shifted. Okay, so you multiply and then you shift the signal, and then you multiply, shift the signal, multiply, compute the DFT, shift the signal, multiply, compute the DFT, shift the signal. And how much you shift depending on this capital R. And you can jump one sample, or you can jump a whole window, for example, or you can jump non-overlapping window. And those will give you, different, basically, it will give you different interpolation of your time frequency signal. Okay? So there's a definite inherent trade-off here. And then we talked about this Eisenberg boxes last time. And this is a concept that takes time to grasp. But effectively, if you have a certain energy concentration in time, there's an energy concentration in frequency, then the area that these have in the time frequency space is constant. Okay? So if I shrink, or it's bigger than something. So if I shrink this and I want to concentrate over a smaller portion of time, I zoom in into time, I have no idea what the frequency is. Okay? Or my uncertainty in the frequency goes down. Okay? If I am interested in the frequency, then I need to capture quite a wide range of time points in order to compute frequencies very well, okay, very accurately. So this is kind of the trade-off. In discrete space, basically, it's broken into it's more simple, in the sense that if we look at the DFT and we look at how the DFT, each one of those DFT coefficients, okay, DFT coefficients are represented in this time frequency space, then they're basically blocks of size n, because that's the size that we capture in time. And then in frequency, they're basically 2 pi over n. Okay? They represent that kind of frequency. Okay? So this is approximate. I mean, if you think about DFT coefficient, they have leakage to other frequencies. They're not perfect. But most of the energy is concentrated in those particular frequencies. Then I asked you what happened when you do zero padding, and zero padding doesn't add more resolution in frequency. So what does it do? Yeah, it's basically shifts. It's interpolation. So each coefficient of a zero padded, let's say a zero padded by a factor of 2, each coefficient will represent now a center frequency around this point, not here, in the middle, but its uncertainty is still the same size. Okay? Its uncertainty is the same size. It doesn't look sharper. There was, my ability to resolve between two frequencies within this range is not existent. Okay? I can separate between frequencies in this range, but I cannot separate within that range. Okay, any questions? Okay, then we went into talking about what happens in the time-dependent Fourier transform, the discrete short-time Fourier transform. In that case, we now break the time-frequency space into blocks, as opposed to just, how do you call them? These rectangles. We break it into different blocks. It's just a different decomposition. Okay? So that my time frequency space now is broken into time blocks. So now I have better locality in time, but now I trade off that locality in time and uncertainty in frequency. The size of the block in area is the same. Okay? And if I want to expand, then I lose the other. Okay? What happens then if I use different, so R is optional, but if I use, let's say, overlapping blocks, what would be the case then? How would the time frequency space be tiled? If I use overlapping blocks? Offset in time, but same size. What if I zero pad the DFT? It will be overlaps in frequency. But the size of the block is going to only depend on the time and frequency that you're going to be using. So it's not going to change. Okay? All right. So then I had this examples, like a spectrogram of an orca. You look at the dynamics of different frequencies that happen at different times, and the choices that you make will enable or not enable you to distinguish between those frequencies and those rapid changes. Okay, if something changes rapidly both in time and it has very high resolution frequencies, there's no way that you would be able to resolve. There's going to be certain uncertainty that you'll be able to resolve or not. Okay? So I gave you this example, and when you have two different windows, okay, this one is a window that has more leakage. So this is a rectangular window. This is a Hamming window. You see the difference in those type of windows. Okay, and so this is with a Hamming window. This is with a rectangular window. This has a better resolution, slightly better resolution, twice as good than this one. But this one has much less leakage, okay, to the other ones. Then I had this example where we look at these two spectrograms, and now you see beautiful resolution and frequency. Okay, but the resolution in time is not great. Okay, when things are changed, you can't really see them change very well. You see, it's kind of like blocky. It's blocky over time, but here, look how nice it is. But here, I cannot resolve those individual frequencies. So the difference between the two here is that here, I used a larger window that allowed me to resolve frequencies better, but I lost the time resolution. Here, the opposite. Okay, I have better time resolution, but I lost the frequency. And ultimately, if I had something that changes really rapidly, but also has a higher resolution frequency, there's no way I would be able to distinguish. No matter what I do, there's going to be a limit to what I can resolve. Okay? And the difference between these two is, again, is described by the DTFT of the Hamming window, which is effectively when you use a smaller window, like a 32, then it's pretty wide. When you use a 64, then it's half as wide. This is also called a point spread function. Okay? I don't know if you heard this before. But basically, any single frequency like that exists in the frequency domain, when we use this window, it is going to be blurred by this spread function. Because it's going to be convolved by it. Okay, that's why we lose resolution. So it's also called a point spread function, okay, which is really kind of an impulse response. In this case, it's an impulse response in the frequency domain. So I don't want to confuse you with these terms. But a point spread function is how a point or a single frequency would be spread, and so I get some uncertainty. Okay. All right. Then I want to talk a little bit about applications. And this is a spectrogram of FM radio. So look how rich it is. It's not just looking at frequency by itself. It's not like looking at the time. This is both time and frequency. I guess this is NPR, so there's a lot of speech. Yeah, there's not much music. So you kind of see the dynamics over time that looks like speech. And because it's frequency modulated, then the intensity is translated into changes in frequency. Okay, frequency modulated. Changes in amplitude of speech is translated into changes in frequency. Okay, so we can see it very nicely. Okay, so it almost looks like the time signal, right? If you think about that, but it's really in frequency space because it's frequency modulation. What is FM? FM is defined the following way. Okay, so A times cosine of a carrier 2 pi FC. This is the center frequency. In this case, is 88.5. Okay, megahertz, plus 2 pi delta F, so the changes, how much variation you're willing to go through, and then integrate over your time signal. Okay? Integrate it over your time signal. Okay? So this will basically define if you have certain amplitude change, then that would correspond to quite change in frequencies. Okay? So if you take the derivative of this, then you just get delta F times x, right? That will be the frequency. Okay? The derivative, this is the phase. The derivative of the phase is frequency. The derivative of the phase in this case will be 2 pi delta F times x, right? So x is the will be the frequency. X times delta F will be the changes in frequency. Right? Derivative of phase is frequency of a cosine. 2 pi f t. You take that 2 pi f t is the phase. You take the derivative of the phase, you get 2 pi f, which is the angular frequency. Okay? So the derivative of the phase is always the frequency. In this case, the derivative will be 2 pi delta f, which is how much you're willing to deviate, multiply your signal, which is then looks like this. Okay? Does this make sense? This is the signal I want to transmit. Your quietness is not really revealing whether I should keep on or explain. Yes?
Why is it that you integrate it? Why couldn't you just use the signal itself?
Oh, if I use the signal itself, then the signal, that will be phase modulation. Because I want to change the frequency with respect to my signal. Okay? So if I don't, then it's just x. So it's 2 pi delta f times x. What is the frequency? Instantaneous frequency is the derivative of the phase, by definition. If I have a constant frequency, right, it's 2 pi f. Because 2 pi ft, that's the phase. Instantaneous is the phase. So the instantaneous frequency, it will be 2 pi f. The instantaneous frequency in this case, if that was not integrated, would be 2 pi delta f times the derivative of x, which is a different frequency. Okay? But that's called phase modulation. This is frequency modulation, because then I have to take the integral. So when I look at the instantaneous frequency, it will be the derivative of this component. Okay? So the derivative of the entire thing will be basically 2 pi fc plus 2 pi delta f times x. That is the instantaneous frequency, corresponding to where you are in the amplitude. So the amplitude will correspond to instantaneous frequency. Does this make sense? If not, think about it. What does it mean, frequency? Okay, its phase changes over time. Okay, so the derivative of that. Okay, so now what we get here are just samples of this thing. Okay, so we get at evaluation of this. So by the way, another way to think about this is looking at the instead of cosine, is looking at just the analytic signal, which is basically the e to the power of that, so the complex value. Okay, that will be then a one-sided spectrum. Okay, turns out the SDR will give you this, and I'll explain why it actually gives you this. But if we look at this, this is what we receive from the software-defined radio. Okay, we get this. Now the question is really, what is x of t? Okay, x of t, depending on, and this is actually interesting because this is how broadcast FM works. X of t is the carrier, is the baseband. It's the baseband. It's really the information that it's sent. Your radio, that's what your radio is going to be decoding. Okay? So x of t is this signal that is going to be frequency modulated. Okay? What they do is they want to send you music, and they want to send you stereo music. So they could have sent you the left channel separately and then the right channel separately and kind of mix them together somehow. The way they chose to do this was to send you on the baseband. So this is not modulated. So x of t is the left plus right channels, which is really mono. Okay? The reason they do that is once I demodulate this, I recover the frequency. So this is frequency modulated. When I demodulate FM, and you're going to do this in one of the labs, you're basically going to get back x of t. Okay? So L plus R is really the low frequency. It's the baseband. That you can actually play. And so radios that don't have stereo, they just do a low-pass filter and just get this component. This is the spectrogram of x of t for a station playing Adele. So this part over here, this is the low frequencies, changes over time. This is the left plus right channel. What they did then is, if you want to actually listen to stereo, they're going to transmit what's called a pilot. It's a pure frequency, it's 19 kilohertz. if you want to play music, I mean, we cannot hear 19 kilohertz. So what they do is they low-pass filter this, and they just play you the mono music. Okay? This is inaudible. Okay? What they do then is they use this frequency, double that frequency, to AM modulate, amplitude modulate, the left minus R channel. That gives you the stereo component. This is stereo component. Okay, the difference between the two channels. So now, if you know this and you know this, you can then play stereo. You can play the left and you can play the right, because you have L plus R and L minus R. So you can play them. And what you use is you use this frequency in order to demodulate this one. And then up at 3 times the pilot frequency, there's tiny signal over here. That's the digital information of the station. Some radios are able to display, the song and stuff. So that's encoded over here at 57 kilohertz. So all this signal is then FM modulated. Okay, so this is how it looks. L plus R, pilot, L minus R, RBDS. Okay? But then, you listen to tune to 94.1, which is KPFA. It's a station up on the hill. It's a Berkeley station. And now I look at the spectrogram of the demodulated FM signal. And this is 0 frequency. That's the L plus R. You see how it changes over time? Okay, that's the L plus R. That's while playing Adele or something like this. You don't hear this, though. You hear something else. I'll tell you what you're hearing. This is the pilot that I was mentioning. You see? That's the pilot. 19 kilohertz. Then the L minus R stereo. Okay? That's the stereo. Then you've got here at 54 kilohertz, you've got the RBDS. That's the digital information. But check it out. At 67 kilohertz, there's something that looks to be FM modulated. And then at 92 kilohertz, there's another FM modulated signal. These are called, if you actually look at Wikipedia, these are called subcarriers. Is that the stations, they rent those parts for other stations to transmit information. And so if you have a radio that can actually decode these subcarriers, you can listen to them. This one, particular one, is French Haitian. That's where you're hearing. And this one is Punjabi radio. Okay? And one of the labs will be to decode that. You'll be able to do something like this that no radio could do unless it's a specialized radio, but with these dongles that we're giving you, you'll be able to decode those. Okay? There's not a lot of subcarriers. In Europe, actually, they use them to transmit information to bus stations, to transmit commercials and things that will display on bus stations. So it's kind of like a way to use some sort of a transmit already to transmit, but nobody can hear it unless they could decode it in this particular way. Okay? Yeah.
For the stereo, what do you have, two trapezoid, on the graph there?
Yeah, because it's AM, amplitude modulation. So when you amplitude modulate, then you take something that has 2 bands, and then it displays, it's translated, right? That's the positive and negative frequencies. Actually, all the information is here. You could use just 1 band, but it's just much simpler to demodulate that. Okay. Here's another application. This is digital, spectrogram of digital data. So it's frequency shift keying. So you transmit bits by changing frequency. So this is 1, -1, 1, -1, and you can kind of switch between frequencies. Okay, I picked it up from some frequency. I'm not sure even what. Okay, so now, let's say you have a spectrogram. You computed a spectrogram. Now you have this 2-dimensional space. How do you go back into the time domain? Okay, how do we reconstruct? So as it turns out, for non-overlapping windows, what you could do is you take the result. Okay, if you actually think what it actually is, then for a particular n and particular, for a particular n that you have, you just take the inverse DFT, right? This is basically a DFT of a certain window, right? So I just take the inverse DFT of this one column. Okay. So for a particular n, I can take the inverse DFT. That corresponds to a single window, single chunk of data or a block of data multiplied by a window. If I want to reconstruct the time signal, I need to divide by that window in order to equalize it, right? If you think of what I computed, can everybody see this? I have a certain signal. I chunked a box out of it, or a block. I multiply it by a window, and I computed the DFT. To reconstruct, I take the DFT, I take an inverse DFT, and then I need to divide by that window in order to make it flat again. Okay? Non-overlapping windows. Okay? What's the problem? What about that sample over here?
0.
Right? It's not stable. Right? It is 0 or close to 0. If I did some processing on the spectrogram that I could do, now any small changes that occurred here will be amplified much more than they should be, because I'm going to divide by something which is small. Okay, so it's going to amplify. So that is a problem. So what you could do, if you want to do a stable reconstruction, is you want to overlap the windows at least 50%. If you do that, and you use, for example, a Han or a Bartlett or a triangular window, then you don't even need to divide, because overlapping them will give you exactly 1, a weighting of 1. Okay, so if you overlap windows like this, then any processing that you need to do, you basically just take the inverse DFT and then add them together with the according, the right shift. Okay, so you get a perfect reconstruction. Well, not a perfect reconstruction, but you get a stable reconstruction. But here's an application like where you could actually use this for. Let's say you want to do noise removal, and let's say you have noise on this bird signal. Okay, you've got noise. Noise, if I want to, I know what the spectrum of the chirp, right? Of the bird signal. I know what the spectrum. I can compute it, and then I can maybe filter it. Okay, I can filter those frequencies and get rid of some of the noise at the low frequencies and the high frequencies, for example. That's one way, but it's not perfect. I know that the bird signal changes frequency over time, so I'm not really using all my information to remove noise. If I compute a spectrogram, now, if you think what would happen to noise, noise will be everywhere. But what did I do to my signal? My signal is now sparse. Right? My signal is sparse in this multidimensional space. How would you remove noise? Yeah. Mask it. So threshold, right? Is that what you meant? So I can threshold this signal. That will give you just the simple operation of thresholding, gives me effectively an adaptive filter. If you think about this, an adaptive filter that adapts to the signal, right? And will be kind of like a bandpass filter, right? If I threshold, then I would just go around. And if you think about this is automatic adaptive filtering that would occur if I just do this nonlinear operation of thresholding in this domain. So it's really powerful, okay, for this particular type of signals. The Orca signal would have been more difficult, right, because it's more spread out. Okay, but still, maybe we could do something about it. So that allows you to do very interesting type of processing. So what you could do is threshold, and then perform a stable reconstruction. You got yourself a much cleaner signal. Okay, very powerful. Sparsity, extremely powerful. Some people can make careers out of it. Okay. So the limitation of discrete short-time Fourier transform is that you need overlapping. When you need overlapping, it's not orthogonal anymore. You start with n number of coefficients. You end up with 2n number of coefficients. When it's non-overlapping, it's n to n. But now it's n to 2n. So, there's things that you have to take into account in terms of the reconstruction. What does it mean? And so on and so forth. Okay? It is more computationally intensive. So the computation is O of m times n log n. So m is the number of blocks. Yes. Right? The number of blocks that you're going to be using. Okay, so it is more computationally intensive. And one of the other limitations is that you are using the same size of Eisenberg boxes. So you split the grid of time frequency space into rectangular boxes. That may have some limitations, which we're going to deal with when we go to talk about wavelets. Okay? But I don't want to talk about wavelet today. We'll save it to next week. What I do like to talk is about the lab one. So before that, is there more questions? Yeah.
When you say thresholding, what exactly do you mean? Like you cut off like values below certain points or what?
Yeah, so let's say I know, here's a simple case, right? Let's say I have a certain sinusoid. I don't know what it is. I have a signal, which is a sinusoid. It's just one. I don't know what it is, though. Okay? I don't know what it is. Okay? But the problem is that's really noisy. It's buried in noise. How can I clean this? Well, a low-pass filter, I might filter that signal because I don't know what the frequency is. It could be anywhere in the spectrum. What do I do? Well, if you compute the DFT, what the DFT does, it will take the sinusoid and make it into two delta functions, right? Or two spikes that are quite large. Way above the noise. It's kind of like a broomstick that will take the signal and put it in this one large coefficient, right? Now it's going to be above the noise. Okay? So now, after you did that, then you can do filtering. But you have to do adaptive filtering, like it depends on the signal. So that's nonlinear. So one way to do this is set a threshold, and then anything below the threshold might be a signal, anything below that threshold is noise. Then you take an inverse DFT and you get back your sinusoid. Yeah. Yeah. Statistically, you can kind of pick up, and that depends on, it's going to be a trade-off between false detection and false alarm and all sorts of other statistical considerations. Okay? Yeah.
This is a bit earlier, but these Heisenberg boxes,
yep.
what their dimensions is like 2 pi over L times L.
They have this, right?
Yeah, which you multiply, and it's not 1/2.
It's not 1/2. It's 1/2 is in the continuous case.
Okay.
In the discrete case, we said it's 2 pi.
So 2 pi is the best you can do?
Yeah. 2 pi over n. Right? So, it's the size of it, yeah, that's right, 2 pi. That's right, 2 pi. So this is, go back to your question. That was a way to denoise, for example, a sinusoid, but it only works if it's like one sinusoid. If it's like n sinusoid, then, there's no really threshold because everything I'm going to threshold is going to be also signal and noise. So that's not going to work. Okay? So for this particular case of the bird, doing a spectrogram is a good way to represent the signal in a sparse way that allows us to maybe separate well between signal and noise. We're going to talk maybe in the last lecture about, what are the implications of sparsity. Yeah. Sparse, there's just a few non-zero coefficients. Okay? So if you have some spikes in time, that's a sparse signal. If you have a few frequencies, that's sparse in the frequency domain. If you have this chirp signal, that's sparse in time frequency domain. Okay? It's not sparse in frequency because it covers all the frequencies, right? It's not sparse in time because it's always happening, but it's sparse in time frequency space. And as you'll see, the wavelet transform turns also to sparsify signals. So that's why it's really powerful when we talk about denoising. It sparsifies well natural signals, and we'll talk about that when we get to it. Okay? All right, I want to switch back and into talking about the lab, and I hope I'll have time to go over everything. So I'm going to go quite quickly, okay? About 15 minutes. So the thing that we need to cover in the lab, the first thing you're going to do is look at a chirp. Why chirp? Chirp is a very interesting signal because it changes frequency in time. So time corresponds to frequency, and frequency corresponds to a particular time. Okay? So if you think of me moving in time, okay, it's also changing frequency in the same way. It's a linear chirp. It's called a linear chirp. If you look at a spectrum of a chirp, it's constant. Why? Because if I look at all the frequencies across a certain time, yeah, it just went through all of them. So there's energy in all frequencies, equal amount of them. So it's a really interesting signal. Okay? If you want to generate something that has all frequencies, and you don't want to use a chirp, you use a delta function, for example, right? Or a sync if you want a large bandwidth, right? But this is very different than a sync, but still has similar characteristics. Okay? A sync function, right, would have a bandwidth, like constant frequencies over a certain bandwidth. This also has a constant frequency over bandwidth, right? But it definitely doesn't look like a sync, okay? Which is interesting. Now, what's interesting about a chirp is because we change frequencies over time, we can use it to probe a system for its frequency response. Okay? So what is the frequency response? You put a frequency in, you measure what is the amplitude and phase that comes out. If I now sweep frequencies and I measure the response, I get the frequency response. Okay? So that's one way to compute a frequency response. I could have, for example, computed the frequency response of what the targets here is to see what the frequency response of your speaker and microphone system. Okay, so you transmit some signals you want to pick up, and so you're in a room. There's going to be some frequency response of the room, the speaker, the microphone. All of them together will turn out into a frequency response. I could have just sent a pulse. The problem is that the speaker is not able to produce a good pulse. But if I send frequencies and I change them slowly, then I could look at the frequency response. So this is what you're going to do. Okay? So what you're going to do is you're going to play and record a chirp. You're playing a chirp and recording it, and this is the absolute value of what I recorded. Okay? This is the result. Okay? Of what I recorded. This is a time signal. A time signal. Okay? I look at the frequency, and this is the absolute value of the time signal. Then I compute the DFT of the time signal that I get. Looks the same. Because it's a chirp. Frequency corresponds to time. It's exactly this, there's this beautiful analogy. So if I look at the frequency response, yeah, I get this beautiful similarity between these two. Okay? Which is cool. Then what I could do, and the thing that you are going to do, is you're going to take this time signal, and because it's because we did a chirp, then it's like has lots of oscillations here. We're just going to look at its envelope. Okay? So one of the way to look at the envelope, you could do that by a low-pass filter, and there's other ways that you could do this. But one way is to use the Hilbert transform. Okay? And there's an explanation in the lab. Why is that? You basically look at the analytic function, which turns sines and cosines into e to the power, okay? Which have a unit amplitude. Okay? So then you basically, this is one way to look at the envelope of the signal. Okay? So there's description in the lab of how to do this and why it actually works, and there's some mathematical derivation of that. But effectively, you can look at the envelope of this, and it looks exactly like the frequency, which is kind of cool. So this is the frequency response, and this is from my laptop. Okay? So it's really loud, and the audio, like the speech. Okay? It's not just the speaker, it's also the microphone together multiplied. So it's kind of hard to differentiate between. There's actually no way to differentiate. And it also depends on the room. And if you change it slow enough, then all these transitions, that reflections that happen, they don't contribute much. Okay, you get a steady state response. We're assuming that things are not changing over time when we do that, or they're changing much slower than we're sweeping the chirp. Okay. The other thing that's interesting in a chirp is that it has a property called pulse compression. So if you take a rectangular window and you convolve it with itself, this is called an autocorrelation. You convolve it with, actually you flip it and convolve it with itself, but because a rectangular window is symmetric, it doesn't matter. But so if you just overlap a rectangular window, what do you get? A triangle. So you get a spread, right? And the maximum signal is always in the middle. Okay. In this case, we look at pulses that look like a hand window, and so the autocorrelation of these pulses is basically kind of like a hand window spread. Okay, so it's a hand window with itself. It's something that spreads out. It kind of looks like this. So if I take a pulse with a constant frequency, and I look at its autocorrelation, it's going to have twice the width of the pulse. So if I use a pulse of length 500, the autocorrelation will be 1,000. You heard the -1? Because that's discrete. Don't forget that. But when it's large enough, it doesn't matter much. But you have to track all these numbers. Okay? With a chirp, it has this interesting property that when I look at the autocorrelation, it's actually energy is concentrated. It is spread out. There is energy here, but most of the energy is compressed. Okay? This is why it's actually used in radar. Because when you send a pulse, and the pulse returns back, and you want to detect it, often what you do is what's called a match filtering or autocorrelation with what you sent. If it looks like this, then it's kind of spread out. You get low resolution. If you send a chirp, it comes back, you get high resolution because it has this pulse compression effect. So it's very, very useful. Okay? Noise actually behaves the same. If I could send noise, it will return, and we do an autocorrelation, it will be a delta function with very little interference. Okay? So noise has a similar property, but a chirp is really easy to produce as opposed to noise. Noise is not produced really well here, but a chirp is. Okay, so what you're going to do now is generate a pulse, and you're going to change the analytic function of a pulse. So e to the j something, and you're going to play the real part of it. And you're going to play a pulse. You're going to generate a pulse train, and you're going to transmit and record. So this is what I transmitted. And this is what I recorded. And when you zoom in, you see that I transmitted this that looks like that. Right? This is just narrow. It's not really just a spike. It's this constant frequency that I sent. Okay, or a chirp. I don't know what I sent here. And then that's what I picked up. There are certain systematic delays as well that's happened. That's why it's a little bit delayed. Because it's just a USB, and all this thing that takes time. But basically, this corresponds to this one. That's a spike that, from the microphone to the speaker that went through directly. So this is the part that went directly. But what are all these other parts? Where are these coming from? These are echoes that bounce back from different objects in the room. So I can see them, I don't see them very well. So what I'm going to do is I'm going to do a match filter with basically an autocorrelation with what I sent. If I do a match filtering with this is what I get, and I look at its envelope. That's why you're using the analytic function, because it's easy. Again, it's like a Hilbert transform that lets you look at the envelope. So that's what I receive. So any peak here is, in fact, an echo that comes back, which is kind of cool. So now what I can do is I can send a bunch of pulses repeatedly, and when I do that, this is a pulse, and what I get. This is a pulse. They're all aligned. And you see that at some points there's reflections that occur, corresponding to distance. Time corresponds now to distance. The time of arrival is how far they went and came back. Okay? So this is in samples, but you can translate samples into distances. And you now created a sonar, okay, using a computer. And then if I move stuff around, it's going to look like this. You know? This is where I moved the laptop, and my ceiling reflected those frequencies. Now Frank did an amazing job of allowing you to do an interactive, to make this interactive. Last year we didn't have that interactive. This year it's now interactive. And within IPython notebooks, we gave you this interface that allows you, once you write the code for the sonar, to actually see it in real time. So you're going to create this function that would detect these pulses, and you hear the clicks? You hear them? Huh? Come on, this is awesome. Right? It's pretty awesome. What? So now you can also play with different resolutions, because now you can now look at the trade-off of what is the, what's the size of the window, what are the frequencies, all this stuff. Okay, that allows you to kind of look at the resolution. So now the resolution wasn't good. What I'm going to do, so I'm using a 50 length pulse. What I'm going to do now is I'm going to start do it like a chirp. So it has a pulse compression. And I'm going to actually increase the pulse. So what happens actually if I keep this at 10 kilohertz, so you can actually hear it, and then I make it into a 500 length pulse. Hear it? I lost resolution because I make it into 500. You see, it's not very good. So now I really lost my resolution. Oh, what did I do? Stop. Stop. Okay. So the other thing, this is not stable so much. So, you have to restart the kernel sometimes. Okay? So sorry about that, but, that's what we could do. Okay? So now what I'm going to do is I'm going to make a chirp. I'm going to sweep from 10 to 18. So the length is the same, but now I'm going to switch the frequencies. You hear the chirp now? You see that the resolution now increased because of the pulse compression. Look how sweet it is. There you go. You see how well the resolution is improved? Oh, this is awesome. I can play with this forever. Anyway, this is the lab. And it's a really cool lab. So please do it and enjoy it. Okay? All right, but that's kind of the idea. At the end, you're going to do this. Okay, so then in the last, and I'm going to steal 2 minutes, I'm going to talk about why you're going to use SDRs. And the SDRs have complex samples. The samples that you get from the software-defined radio are complex. It's like, oh, it's complex. These signals are real. It's not possible. So if you look at the spectrum of FM, right, it has real and it has the positive frequencies and it has negative frequencies. When you receive like RF, it has negative and positive frequencies. That's why signals are real. Okay. What the SDR actually gives you is a sample representation of this part of the spectrum. Okay? It's a representation of this part of the spectrum. Okay? Now, if you just want to look at this part of the spectrum, you stare at this, it's not symmetric. If it's not symmetric, it has to be complex. It got to be complex. Okay, so if I just look at this, the SDR gives you a sample representing this. If I take the Fourier transform, I only see this. How does it do this? You know how you do this? It's really easy. You take the RF and you multiply by e minus 2 pi f0t. There's no such thing. And then you low-pass filter. So that takes this into DC, and then you filter it out. Right? Do I have animations for this? Yeah. You modulate. That shifts the spectrum. Right? And then you low-pass filter. Gets rid of that. And then you just digitize it, right? Look, I'll do it again. Oh. And then you sample. You sample this. Trivial, right? And I've seen PhD student in quals telling me that they could do that. And I was like, well, how can you multiply by e to the minus 2 pi? And I was like, yeah, that's a problem. How can you multiply by e to the minus 2 pi? Well, what you do is you split into two. You multiply by a cosine, and then you multiply by a sine. You low-pass filter this guy, low-pass filter this guy. You digitize both, and this would be the quadrature component. That's the imaginary representing the imaginary component. This one representing the... And this is actually what your SDR will do. Okay? So what happens is, when you multiply by cosine, you get this. They overlap. You get this, you get that side plus this side. Then low-pass filter, you get this. When you do the other side, then it's flipped and then multiplied. Right? So then you get this part. And both of them together will be effectively like e to the minus j. Okay? If you look at what the chip does, look at this. This is the demodulator. It goes through these two mixers, and then low-pass filter, analog to digital is exactly the same thing. It actually implements this. So this is why these are complex. Okay. Now, what you're going to do is you're going to look at spectrum. So you're going to tune to NOAA weather radio frequencies. It's transmitted from Mount Diablo and from Mount Tam. And then you're going to listen to 162 megahertz. And you're going to compute the frequencies. This is NOAA radio. And then you're going to compute a DFT of 8,000. You're going to get this. It's kind of noisy. Then you're going to break it into windows and average them to improve. But you lose some resolution, but you get better signal-to-noise ratio of those frequencies. Then you're going to look at a spectrum of FM. It looks like this. This part is HD radio. And then finally, you're going to do something really cool. Airplanes transmit their position in what's called, in packets at 1090 megahertz. So somebody will interrogate them, and then they'll transmit the position. 1090 megahertz. Your SDRs could do this. The rate that they're transmitting packets is 1 megasamples per second. And you're sampling at 2 megasamples per second, so it's almost Nyquist rate. So you can actually recover this. Each packet in what's called ADS-B mode S packet has a preamble of 101, da-da-da-da-da, 101, da-da-da-da-da. That's the preamble, and that's the packet. The packet is encoded with what's called amplitude shift keying, which if you transmit, that's on. If you're not transmitted, this is 0. But the way they do this is actually they look at a chip over bins of frequency, and they call it Manchester coding. Instead of sending on or off, what they say is within a certain time, if it changes from on to off, that's a 1. If it changes from off to on, that's a 0. Okay? So you got all these transitions all the time that's happening. That's why this is called Manchester coding, and it allows you to lock into the rate of the code because there's always transition. This is real data. Look, it matches. Not perfectly, but it does match. If you acquire 1 second of this signal, you see, I got all these transmissions. What you're going to do is you're going to pick them and then get bits out of them. Okay? So you're going to decode bits. You're going to do some trick to estimate the noise. You're going to set some threshold. You get those packets. You're going to decode it using certain ways to figure out whether you're actually locked into the preamble. Once you get the bits, we'll give you software that will allow you to put it on Google Maps. Okay, and decode those packets. Okay, so then I think it will be quite cool. There's different TAVO packets, but only the long ones give you the position. The short one don't. Okay, so I think this is also an exciting, thing. Do it outside when you actually capture. Don't do it inside. You don't get anything. There's no planes inside. Have fun. See you on Friday. Please come midterm, right? You have to come.